October 24th, 1944. The waters off Samar Island, Philippines. Rear Admiral Tomiji Koyanagi stood on the bridge of the heavy cruiser Tone, watching distant shell splashes erupt from the sea nearly 40,000 yards ahead. His optical rangefinders, the finest equipment Japanese industry could produce, confirmed what seemed impossible. American battleships were firing at ranges exceeding 24 miles. At this distance, Tone's own guns could not respond. The shells fell like rain from an invisible storm, originating from warships beyond the horizon, beyond visual detection, beyond any range Japanese naval doctrine had prepared for. This cannot be standard capability. No navy builds battleships that can engage at these distances. The Americans must be using experimental weapons, desperate measures from a fleet we were told was in retreat. What Rear Admiral Koyanagi did not yet comprehend, what would take months for Japanese naval intelligence to fully accept, was that these ranges were not experimental or exceptional. They were routine capability, built into every Iowa-class battleship from their initial construction. The Americans had not merely built faster battleships. They had created warships that could engage enemies from distances that rendered Japanese counterfire impossible, that could strike before Japanese forces even knew they were under attack, that transformed naval gunnery from visual art into mathematical science, executed by machines calculating trajectories. No human mind could compute quickly enough to matter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The shells screaming toward Koyanagi's task force that October morning represented the culmination of American naval engineering philosophy, applied without compromise to the problem of decisive surface combat. Each 16-inch armor-piercing projectile weighed 2,700 pounds. Each contained explosive filler that could penetrate the thickest armor plate any battleship carried. Each had been fired from guns elevated to angles approaching 45 degrees, sending them on ballistic arcs that reached altitudes of nearly 50,000 feet before descending toward targets the gunners had never seen with their own eyes. The Iowa-class battleships USS Iowa, New Jersey, Missouri, and Wisconsin represented American naval power in concentrated form. Each displaced 45,000 tons standard, 57,000 tons fully loaded, each stretched 887 feet from bow to stern. Each carried 9 16-inch guns in 3 triple turrets, capable of throwing shells weighing more than a ton each to distances exceeding 42,000 yards under optimal conditions. But the numbers alone failed to capture what made these ships revolutionary. The Iowa class was designed from the keel up, around capabilities Japanese battleships could not match. Speed of 33 knots, faster than any battleship Japan possessed. Fire control systems integrating radar tracking with mechanical computers. Electrical power generation sufficient to operate dozens of radar sets simultaneously. Interior layouts optimized for damage control that could keep the ships fighting even after absorbing punishment that would have crippled earlier designs. Every system aboard these vessels reflected lessons learned from years of combat, incorporated into designs that anticipated future warfare rather than perfecting past traditions. The journey to this moment had begun years earlier, in the design competitions and technical debates that shaped American battleship development during the late 1930s. The Washington Naval Treaty of 1922 had limited battleship construction among major powers, imposing tonnage restrictions and gun caliber limits that shaped naval architecture for nearly 2 decades. When treaty limitations finally expired in 1936, American naval architects faced fundamental questions about what kind of battleship would dominate future combat. The Navy's preliminary design studies explored multiple configurations: fast battleships capable of operating with carrier task forces, heavily armored battleships optimized for gun duels with enemy capital ships, compromises balancing speed, armor, and firepower. The debate centered on whether battleships would primarily fight other battleships in traditional line actions or whether they would serve as escorts for carrier forces that would decide naval supremacy through air power. Captain William Callahan, head of the Bureau of Ships Preliminary Design Section, argued that future battleships needed speed sufficient to escort carriers while maintaining firepower adequate to destroy any enemy battleship they encountered. His philosophy held that American battleships should be able to choose when and where to fight, using superior speed to control engagement ranges and superior fire control to strike at distances where enemies could not effectively respond. This approach required accepting some reduction in armor protection to achieve the required speed and maintain firepower. The design that emerged from these debates became the Iowa class. Construction authorization came in 1939, with the first ship, USS Iowa, laid down at New York Navy Yard in June 1940. The design emphasized speed and firepower over maximum armor protection. The main battery of 9 16-inch guns matched the heaviest armament any battleship carried. The speed of 33 knots exceeded any existing battleship by at least 3 knots. The armor scheme provided protection against 16-inch shells at battle ranges, accepting vulnerability at very close ranges where engagements were considered unlikely. But the revolutionary element was not the guns or armor or speed. It was the fire control system, designated the Mark 38 Director with Mark 8 ranging radar. This system integrated optical range finding with radar tracking and fed data to Mark 1A fire control computers that calculated ballistic solutions automatically. The computers compensated for ship motion, wind speed, air density, powder temperature, and dozens of other variables that affected projectile trajectory. Human operators monitored the system and selected targets, but the actual calculation of firing solutions happened faster than any human crew could achieve through manual methods. The Mark 8 fire control radar could track surface targets at ranges exceeding 40,000 yards, providing continuous range, bearing, and rate of change data even when targets were beyond visual detection or obscured by smoke, darkness, or weather. This capability transformed naval gunnery from an art dependent on human judgment into a science executed by mechanical precision. Gunners no longer estimated range through optical coincidence rangefinders and manually calculated elevation. They simply maintained radar lock on targets, while computers automatically adjusted gun barrels to compensate for every factor affecting accuracy. The integration of radar with mechanical computation removed human limitations from the targeting cycle. Human reaction time, calculation errors, and estimation mistakes no longer degraded accuracy. The fire control system processed information and adjusted aim faster than the most experienced gun crews could achieve through traditional methods. This meant Iowa-class battleships could maintain accurate fire at ranges where optical systems provided insufficient data for effective gunnery. Lieutenant Commander Kiyoshi Inoue, a gunnery officer aboard the battleship Nagato, had studied American naval technology through intelligence reports and translated technical documents before the war. His pre-war assessments noted that American fire and control systems appeared more automated than Japanese equivalents, but he had concluded this reflected American preference for mechanical solutions over trained personnel. Japanese doctrine held that well-trained gun crews using superior optical equipment would outperform automated systems that lacked human judgment. This assessment was based on experience showing that Japanese gunners consistently achieved first salvo hits at ranges where American pre-war gunners struggled. The assumption proved catastrophically wrong. American automation was not replacing human judgment with inferior mechanical approximation. It was eliminating human limitations that no amount of training could overcome. Mechanical computers calculated trajectories with mathematical precision. Radar provided range data more accurate than the finest optical rangefinders. Servo mechanisms adjusted gun elevation faster than the strongest manual crews. The compound effect was that American battleships could engage targets at ranges where Japanese optical fire control simply could not function effectively. The first Iowa-class battleship, USS Iowa, was commissioned in February 1943. Her shakedown cruise revealed capabilities that exceeded design specifications. Speed trials demonstrated sustained speeds of 33 knots with reserve power for sprint speeds approaching 35 knots in emergency conditions. Main battery accuracy tests showed that the Mark 38 fire control system could achieve hit probabilities at 30,000 yards that matched or exceeded optical fire control at 20,000 yards. The ship's massive electrical generating capacity supported simultaneous operation of multiple radar systems without degrading performance. USS New Jersey, commissioned in May 1943. USS Missouri followed in June 1944. USS Wisconsin completed the initial 4-ship class in April 1944. 2 additional Iowa-class battleships, USS Illinois and USS Kentucky, were laid down but never completed, their construction suspended after Japanese surrender made them unnecessary. The 4 completed ships formed the backbone of American surface striking power for the remainder of the war. The Iowa class entered combat during operations in the Pacific that demonstrated their overwhelming advantages over any battleship Japan could field. Their speed allowed them to operate as integral parts of carrier task forces, providing anti-aircraft defense and surface action capability without slowing the formation. Their fire control systems allowed them to engage shore installations and surface targets at ranges that kept them beyond effective counter-battery fire. Their damage control systems and compartmentalization meant they could absorb damage that would have crippled earlier designs and remain operational. But the true test would come in surface action against Japanese capital ships. Japanese battleships represented formidable opponents by any measure. Yamato and Musashi, the largest battleships ever constructed, displaced 72,000 tons, fully loaded, and carried 9 18-inch guns, firing shells weighing 3,200 pounds each. Their armor protection exceeded any other battleship afloat, with belt armor up to 16 inches thick and turret face plates 18.5 inches thick. These ships had been designed specifically to overmatch any battleship an enemy could build within treaty limitations. The Nagato-class battleships, though older and smaller, carried 8 16-inch guns and had been modernized with improved fire control and anti-aircraft batteries. The Kongo-class fast battleships could reach speeds of 30 knots and carried 8 14-inch guns with excellent optical fire control equipment. By conventional measures of armor, armament, and crew training, Japanese battleships matched or exceeded most battleships in service anywhere in the world during the early 1940s. Japanese naval gunnery doctrine emphasized perfection through intensive training. Gun crews drilled relentlessly in range estimation, ballistic calculation, and rapid salvo execution. Officers spent years mastering the complexities of fire control, learning to judge range through optical rangefinders and calculate firing solutions through manual plot boards and mechanical rangekeeper devices. The doctrine assumed that engagement ranges would be determined by visual detection limits, typically 15 to 25,000 yards depending on visibility conditions, and that gunnery would be decided by crew training and optical equipment quality. This doctrine had produced impressive results in pre-war exercises and early war engagements. Japanese gunners had demonstrated the ability to achieve rapid salvo accuracy at ranges where many navies struggled. But the doctrine assumed both sides would fight under similar technological constraints. It assumed engagements would occur at ranges where optical fire control could function. It assumed that superior training and equipment quality would determine outcomes. Every assumption would prove obsolete when facing Iowa-class battleships equipped with radar fire control. The Battle of Samar on October 25, 1944, brought these assumptions into collision with reality. Vice Admiral Takeo Kurita commanded Center Force, a powerful surface action group built around the battleships Yamato, Nagato, Kongo, and Haruna, supported by heavy cruisers and destroyers. His mission was to penetrate Leyte Gulf and attack American landing forces, supporting the invasion of the Philippines. The operation required transiting San Bernardino Strait during darkness, then sweeping south at dawn to catch American transports at anchor. American intelligence had detected the Center Force's approach. Carrier aircraft had struck the formation repeatedly during its transit, through the Sibyan Sea. sinking the battleship Musashi through sustained air attacks that demonstrated American air power could overwhelm even the most heavily armoured targets. But Kurita pressed on, convinced that reaching the landing forces would justify any losses. His ships emerged from San Bernardino Strait shortly after midnight on October 25th and turned south toward Leyte Gulf. What Kurita did not know was that American dispositions had changed. Admiral William Halsey had taken the main carrier striking force north, pursuing Japanese carriers in what would become the Battle off Cape Engano. This left the approaches to Leyte Gulf defended by escort carrier groups designated Taffy 1, Taffy 2, and Taffy 3, light forces intended to provide air support for ground operations rather than fight surface actions against battleships. The escort carriers were slow, thin-skinned vessels carrying small numbers of aircraft optimized for ground support rather than fleet defense. At 06:45 hours on October 25th, lookouts aboard ships of Taffy 3 spotted pagoda masts on the northern horizon. Rear Admiral Clifton Sprague, commanding Taffy 3, initially believed these were American battleships until Japanese shells began landing near his carriers. Centreforce had achieved complete tactical surprise, emerging from San Bernardino Strait hours earlier than American intelligence had predicted, and approaching the escort carriers from an unexpected direction. Sprague's force consisted of 6 escort carriers, 3 destroyers, and 4 destroyer escorts. Against them, Kurita deployed 4 battleships, 6 heavy cruisers, 2 light cruisers, and 11 destroyers. The Japanese advantage in surface combat power was overwhelming. Yamato alone displaced more than all 6 American escort carriers combined. Her 18-inch guns could destroy an escort carrier with a single hit. The situation appeared desperate. Sprague ordered his carriers to launch all available aircraft, turn south, and make maximum speed while laying smoke screens. The destroyers and destroyer escorts were ordered to make torpedo attacks to disrupt Japanese pursuit. These were delaying actions, attempts to buy time for the escort carriers to escape, rather than serious efforts to damage battleships with torpedoes fired from destroyers. Centreforce increased speed and opened fire at approximately 27,000 yards. The Japanese formation split into divisions, attempting to envelop the fleeing American force from multiple directions. Yamato's 18-inch guns began landing shells near the escort carriers, sending up massive splashes that dwarfed the small ships. Heavy cruisers closed range rapidly, their 8-inch batteries adding to the volume of fire falling around Taffy 3. But the American destroyers executed their attacks with reckless courage. USS Johnston, USS Howell, and USS Heermann charged directly at the Japanese battle line, firing torpedoes and engaging with their 5-inch guns at ranges where their light armor provided no protection. The destroyer escorts Samuel B. Roberts, Dennis, John C., Butler, and Raymond joined the attack. These small ships, displacing less than 2,000 tons each, took on battleships, displacing 10 times their tonnage. The torpedo attacks forced Japanese heavy ships to maneuver, breaking up their formation and disrupting coordinated fire. Johnston scored hits on the heavy cruiser Kumano, forcing her to withdraw. Howell launched torpedoes at battleship Congo before being overwhelmed by cruiser fire and sinking. Samuel B. Roberts engaged heavy cruisers at point-blank range before being destroyed by battleship fire. The attacks did not stop Centreforce, but they bought time for Taffy 3's carriers to escape. Aircraft from the escort carriers struck Centreforce repeatedly with whatever weapons they had available. Fighters strafed battleship superstructures. Bombers dropped depth charges and small bombs that caused minimal damage, but forced Japanese ships to maneuver. Some aircraft made dry runs, pressing attacks even after expending their ammunition simply to force Japanese ships to waste time evading. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At this moment, with Centreforce closing on damaged American carriers and victory seemingly within reach, Admiral Kurita made the decision that would define his career. At 0911 hours, he ordered Center Force to cease pursuit and withdraw north. His reasons remain debated. He believed he faced fleet carriers rather than escort carriers based on the intensity of air attacks. He worried about fuel state after the lengthy approach through the Sibuyan Sea. He feared American battleships might be approaching from the south, trapping his force. Radio reports suggested American carriers were north of his position, presenting opportunities for decisive action. Whatever his reasoning, Kurita withdrew without destroying Taffy 3. The Battle of Samar ended with Center Force retiring through San Bernardino Strait, having sunk 2 escort carriers, 2 destroyers, and 1 destroyer escort, but failing to reach the landing forces in Leyte Gulf. American forces had survived against overwhelming odds through desperate courage and tactical improvisation. But the battle had revealed something that troubled Japanese naval staff when they analyzed the action reports. American accounts mentioned battleship fire at ranges exceeding 40,000 yards. This was dismissed initially as exaggeration or confusion. No battleship could achieve accurate fire at such ranges. Optical fire control became unreliable beyond 30,000 yards. Even the finest rangefinders struggled to provide accurate data at extreme distances, where atmospheric distortion and Earth curvature affected. Observations. The reports persisted. Multiple American ships reported shell splashes from ranges. Their own optical instruments showed exceeded 35,000 yards. The shells had fallen with disturbing accuracy for such extreme ranges, landing in patterns suggesting radar-directed fire rather than optical ranging. When these reports reached Japanese naval intelligence in Tokyo, they were analyzed alongside other combat data that suggested American fire control capabilities exceeded Japanese understanding. Commander Yasumi Doi, assigned to the Naval General Staff's intelligence section analyzing American technological capabilities, compiled reports from multiple engagements where American battleships had demonstrated fire control that seemed impossible using optical systems. The pattern suggested American ships were using radar not just for detection, but for actual fire control at combat ranges. This conclusion contradicted everything Japanese doctrine assumed about radar. Limitations. Japanese radar development had focused primarily on detection rather than fire control. Engineers understood theoretically that radar could provide range data, but achieving accuracy sufficient for naval gunnery at extended ranges required technical capabilities Japanese industry had not mastered. Japanese radars lacked the precision to provide fire control data at battle ranges. They assumed American radar suffered similar limitations. This assumption was proving catastrophically wrong. The truth was that American fire control radar had advanced far beyond detection systems. The Mark 8 radar could track targets continuously and provide range data accurate to within 50 yards at distances exceeding 40,000 yards. This precision surpassed what optical coincidence rangefinders could achieve, except under ideal visibility conditions that rarely existed in actual combat. Combined with mechanical computers that processed this data faster than human crews could calculate manually, American battleships could engage targets at ranges where Japanese optical fire control simply could not function. The Iowa-class fire control system represented integration of multiple technologies into comprehensive capability. The Mark 38 Director housed optical rangefinders for visual tracking when possible, but the Mark 8 radar provided primary ranging data. The radar antenna, mounted in the Director, rotated with the optical systems, ensuring radar and optical tracking remained coordinated. Data from both sources fed into Mark 1A computers that synthesized information and calculated firing solutions. The computers were mechanical marvels, room-sized assemblies of gears, cams, and servo mechanisms that continuously solved differential equations, describing projectile ballistics. Operators input target data, ship motion, wind speed, and environmental conditions. The computers automatically calculated gun elevation and bearing, adjusting continuously as targets maneuvered and conditions changed. Earlier mechanical fire control computers had required human operators to input manual corrections based on observed fall of shot. The Mark 1A integrated radar feedback directly into calculation loops, automatically adjusting elevation for subsequent salvos based on radar detection of splash locations. This closed-loop fire control was revolutionary. It removed human reaction time from the targeting cycle. When salvos fell short, radar detected the splashes and computers immediately calculated corrections for the next salvo. When salvos straddled the target, computers automatically refined aim based on splash patterns. The system functioned regardless of visibility, operating as effectively in darkness or smoke as in clear daylight. Human operators monitored the system and selected targets, but actual execution of firing solutions happened with mechanical precision that no manual crew could match. The effective range of this system exceeded Japanese comprehension. Under optimal conditions, Iowa-class battleships could achieve hit probabilities of approximately 5% at 40,000 yards. This sounds modest, but it meant that a full 9-gun salvo had better than 40% probability of scoring at least one hit at ranges where Japanese optical fire control could barely determine target bearing. At 30,000 yards, hit probability increased to approximately 7% per gun, meaning full salvos had excellent chances of multiple hits. Japanese battleships, attempting to return fire at these ranges, faced insurmountable handicaps. Optical rangefinders required clear visibility to function effectively. Beyond 30,000 yards, atmospheric distortion made optical ranging increasingly unreliable. Manual fire control calculations took time that allowed targets to maneuver between salvos. Without radar tracking, Japanese gunners had no way to detect splash patterns in relation to targets beyond visual range, making fire correction guesswork rather than science. The result was that Iowa-class battleships could engage Japanese battleships from ranges where effective counterfire was impossible. They could open fire at 40,000 yards, land salvos with radar-directed accuracy, and maneuver to maintain range while pounding enemies who could not respond effectively. Japanese battleships attempting to close range would come under sustained accurate fire throughout their approach, absorbing hits before reaching ranges where their own guns could achieve accuracy. This capability fundamentally altered the naval balance in ways that went beyond simple technological advantage. It meant American battleships could choose when and how to fight. They could engage at extreme ranges where Japanese return fire was ineffective, or close to medium ranges where their rate of fire and fire control accuracy provided overwhelming advantages. Japanese battleships lost the ability to force engagements on their own terms, reduced to accepting combat under conditions that favored American capabilities. The psychological impact on Japanese naval officers who recognized these implications was profound. For decades, Japanese doctrine had held that battleships would fight gun duels at ranges determined by visual detection, with victory going to the side with better trained crews and superior optical equipment. Japanese confidence was built on knowing their training and equipment quality matched or exceeded any potential enemy. Now they faced enemies whose technology made training and optical equipment quality almost irrelevant. Superior Japanese gunners using the finest optical rangefinders money could buy simply could not compete with radar-directed mechanical computers calculating firing solutions. The Iowa-class battleships never fought the decisive surface action against Japanese battleships that their designers had envisioned. By the time they entered service, American carrier aviation had already secured control of Pacific waters. Yamato and Musashi, the super battleships designed to dominate gun duels, were both sunk by carrier aircraft without ever engaging enemy battleships. The few surface actions that occurred involved Japanese forces attempting to reach landing zones or disrupt amphibious operations, actions where American battleships provided shore bombardment and close support rather than engaging in gun duels. But the potential was always present. Had Kurita pressed his attack at Samar with full commitment, had he encountered Iowa or New Jersey rather than escort carriers, the battle would have demonstrated Iowa-class superiority in the most direct way possible. American battleships would have opened fire at ranges exceeding 40,000 yards, guided by radar that Japanese optical systems could not match. They would have maneuvered at 33 knots, faster than any Japanese battleship could sustain. They would have absorbed return fire with damage control that kept them fighting even after taking hits. Japanese intelligence eventually pieced together the full extent of American fire control superiority through captured documents, interrogation of prisoners, and analysis of combat reports. By early 1945, the Naval General Staff had concluded that American battleships possessed radar fire control that provided effective engagement capability at ranges up to 45,000 yards under optimal conditions. This was approximately double the maximum effective range of Japanese optical fire control under normal combat conditions. The disparity meant American battleships could engage Japanese battleships from ranges where counterfire was essentially impossible. The conclusion was devastating for officers who had spent careers mastering the art of naval gunnery. Every refinement of technique, every improvement in optical equipment, every hour of training had been rendered obsolete by technology that removed human skill from the equation. Japanese gunners could not compete because they were solving mathematical problems manually, while American computers solved them automatically. Japanese rangefinders could not compete because they measured distance through optical coincidence, while American radar measured distance through electromagnetic waves unaffected by visibility conditions. Captain Tameichi Hara, who commanded destroyer Shigure through multiple campaigns and survived the war, wrote in his post-war memoir that encountering American radar-directed fire was like fighting enemies who could see in darkness while Japanese forces remained blind. He described engagements where American ships opened accurate fire from ranges where Japanese lookouts had not yet detected enemy presence. The shells simply began falling from nowhere, arriving with precision that made evasion nearly impossible because Japanese crews did not know what they were evading until shells were already in flight. This experience was replicated across dozens of engagements. American battleships and cruisers equipped with radar fire control engaged Japanese forces at night or in poor visibility, achieving first salvo hits at ranges where Japanese optical systems could not function. The pattern was consistent enough that Japanese tactical doctrine evolved to avoid surface actions where American radar superiority would prove decisive. By late 1944, Japanese surface forces operated primarily at night, close to shore, where American unwillingness to risk radar-equipped capital ships in confined waters provided some protection. The Iowa-class battleships spent most of their war conducting shore bombardment, providing anti-aircraft defense for carrier task forces, and serving as command ships for fleet operations. They bombarded Japanese positions throughout the Pacific, their 16-inch guns demolishing coastal fortifications from ranges that kept them beyond effective counter-battery fire. They escorted carriers during strikes against the Japanese home islands, their massive anti-aircraft batteries reinforcing combat air patrol in defending against kamikaze attacks. They served as flagships for fleet admirals, their extensive communications equipment and spacious flag quarters providing better command facilities than any other vessels afloat. USS Missouri achieved lasting fame as the location of Japanese surrender on September 2, 1945. General Douglas MacArthur accepted surrender documents aboard Missouri in Tokyo Bay, with representatives of all Allied powers present to witness Japanese submission. The choice of Missouri was symbolic, demonstrating that American naval power had brought Japan to defeat. The battleship that represented the apex of American surface combat capability served as the stage for ending the war she had been built to fight. The Iowa-class legacy extended far beyond World War II. All 4 ships were reactivated for Korean War service, providing gunfire support for United Nations forces. They were modernized in the 1980s with cruise missile launchers and updated electronics, serving through the Cold War and participating in Operation Desert Storm. USS Wisconsin fired Tomahawk cruise missiles and 16-inch shells against Iraqi positions, demonstrating that even 50 years after construction, Iowa-class battleships retained devastating combat capability. But their true historical significance lies in what they represented during World War II. They were the ultimate expression of American naval philosophy, applied to surface warfare. Speed, firepower, and technological superiority integrated into platforms that could dominate any surface action they entered. They were designed not to perfect existing methods, but to change the fundamental nature of how battleships fought. They succeeded brilliantly, creating capabilities so advanced that enemies who faced them struggled to comprehend what they were fighting. Japanese admirals watching shell splashes erupt from beyond the horizon were not witnessing experimental weapons or desperate expedients. They were witnessing the future of naval warfare, executed by opponents whose industrial capacity and technological innovation had leaped years ahead of anything Japanese forces could match. The shells falling from 24 miles away were not lucky hits or unusual circumstances. They were routine capability built into every Iowa-class battleship, representative of systematic American advantage in radar, fire control, and mechanical computation. Rear Admiral Koyanagi survived the war and spent years analyzing what had gone wrong for Japanese naval forces. His post-war writings concluded that Japanese defeat was inevitable once American industrial mobilization and technological development reached full capacity. Individual battles might have been won or lost based on tactical decisions or chance, but the overall campaign was decided by systematic advantages in technology and production that Japan could not overcome through courage or tactical skill. The Iowa-class battleships never had the opportunity to demonstrate their full capabilities in surface action against Japanese battleships. The gun duels their designers envisioned never occurred, but their mere existence transformed the strategic calculus of Pacific naval warfare. Japanese battleships were reduced to secondary roles, their main batteries largely irrelevant against enemies who could strike from ranges where counterfire was impossible. The revolution in naval gunnery, represented by radar fire control and automated computation, was so complete that by war's end, traditional battleship tactics had been rendered obsolete by opponents who had changed the rules of how surface combat was fought. The technical specifications that enabled Iowa-class superiority were rooted in decisions made years before the first shell was fired. In anger, when American naval architects gathered in 1938 to finalize the Iowa design, they faced constraints that forced ruthless prioritization. The London Naval Treaty limited battleship displacement to 45,000 tons standard. Within this limitation, designers needed to maximize speed, firepower, protection, and operational range. Every ton allocated to one capability reduced availability for others. The solution emerged through systematic analysis of what future naval combat would demand. Captain Andrew McKee, serving on the General Board's Battleship Design Committee, argued that speed deserved priority over maximum armor protection. His reasoning was straightforward but revolutionary for battleship doctrine. A fast battleship could choose engagement ranges, using superior speed to maintain distance, while radar-directed guns engaged enemies who could not effectively respond. A slow battleship, regardless of armor thickness, would be forced to accept combat under conditions enemies dictated. This philosophy required accepting vulnerabilities that more traditional designs avoided. Iowa-class armor protection was sufficient against 16-inch shells at typical battle ranges of 20,000 to 30,000 yards, but inadequate against close-range fire or plunging shells at extreme ranges. The belt armor, 12 inches thick at its maximum, provided good protection but did not match the 16-inch belt armor on some earlier American battleships. The deck armor, 6 inches over magazines and machinery spaces, stopped most shells, arriving at normal trajectory angles, but could be penetrated by shells arriving at steep angles from extreme ranges. These compromises were deliberate calculations based on expected combat conditions. American planners anticipated that radar fire control would allow Iowa-class battleships to engage at ranges where their armor was adequate, while preventing enemies from closing to ranges where armor weaknesses became critical. The strategy accepted risk in theoretical close-range engagements that American doctrine considered unlikely, betting instead on technological advantages that would prevent such engagements from occurring. The propulsion system represented similar calculated trade-offs. Generating 33 knots from a 45,000-ton hull required massive power plants. The Iowa-class machinery produced 212,000 shaft horsepower, driving 4 propeller shafts through reduction gearing that converted high-speed turbine rotation to efficient propeller speeds. The machinery spaces occupied enormous volume within the hull, space that could have been used for additional armor or fuel storage. But the speed capability was considered essential for operating with carrier task forces that cruised at speeds exceeding 25 knots. The fuel capacity of over 8,000 tons of oil provided operational range exceeding 15,000 nautical miles at cruising speed, sufficient for extended Pacific operations without constant refueling. This range was achieved partly through efficient hull design that reduced resistance at high speeds. The length-to-beam ratio of nearly 9:1 created a narrow hull form that sliced through water with minimal drag. The bulbous bow, a teardrop-shaped protrusion below the waterline at the ship's bow, reduced wave-making resistance by modifying water flow patterns around the hull. These design elements combined to create battleships that could sustain high speeds for extended periods, capabilities that proved essential in Pacific operations, where distances between bases often exceeded thousands of miles. Iowa-class battleships routinely operated for weeks at sea, conducting shore bombardments, escorting carriers, and responding to operational requirements without returning to port for refueling. Japanese battleships, designed with shorter operational ranges reflecting expectations of fighting near home waters, struggled to match this sustained deployment capability. The anti-aircraft armament reflected lessons learned from early war experience, showing that air attack posed greater threats to battleships than surface action. Iowa-class battleships carried 25-inch dual-purpose guns in 10 twin mounts, capable of engaging both surface targets and aircraft. These were supplemented by 80 40mm anti-aircraft guns in 20 quad mounts and 49 20mm guns in single mounts. The fire control for these weapons integrated radar directors that automatically tracked aircraft and guided guns to intercept points. The 5-inch batteries used Mark 37 directors with Mark 4 radar, providing automated fire control for medium-range anti-aircraft work. The 40mm batteries used Mark 51 directors with optical sights for close-range defense. The integration created layered defense that engaged aircraft at maximum range with 5-inch guns, transitioned to 40mm fire as aircraft closed, and finished with 20mm guns at closest ranges. This system proved devastatingly effective against Japanese aircraft, including kamikaze attacks that Iowa-class battleships weathered with minimal damage. Japanese battleships carried comparable numbers of anti-aircraft guns but lacked the radar-directed fire control that made American systems effective. Japanese anti-aircraft batteries relied on optical directors and manual fire control, requiring gunners to visually track aircraft and manually calculate lead angles. This worked adequately against aircraft making steady approaches, but proved ineffective against aircraft taking evasive action or attacking through clouds and haze where visual tracking was difficult. The disparity in anti-aircraft effectiveness meant Iowa-class battleships could defend themselves and nearby ships with success rates Japanese battleships could not match. The crew complement aboard Iowa-class battleships reflected the technological complexity of these vessels. Standard wartime complement exceeded 2,700 officers and enlisted men, significantly larger than crews on comparable Japanese battleships. The difference stemmed from American doctrine emphasizing damage control and sustained operations. Large damage control parties could respond to multiple simultaneous casualties, fighting fires, controlling flooding, and maintaining combat capability, even after absorbing significant damage. The damage control organization divided the ship into hundreds of watertight compartments that could be isolated if damaged. Repair parties positioned throughout the ship carried equipment for fighting fires, shoring up damaged bulkheads, and pumping out flooded spaces. Communication systems allowed damage control central to monitor conditions throughout the ship and direct repair efforts to critical areas. This systematic approach to damage control meant Iowa-class battleships could absorb punishment that would have sunk earlier designs and remain operational. Lieutenant Commander Joseph Worthington, damage control officer aboard USS New Jersey, described in post-war interviews how the ship's damage control organization trained continuously for every conceivable casualty. Drills simulated fires, flooding, loss of power, and combination casualties, requiring coordinated response from multiple repair parties. The training created crews who could respond automatically to damage without waiting for orders, significantly reducing response time when casualties occurred in combat. This emphasis on survivability extended throughout the design. Redundant systems ensured that single hits could not disable critical capabilities. 4 separate engine rooms, each with its own turbines and boilers, meant the ship could continue operating even if 1 or 2 machinery spaces were knocked out. Multiple electrical generating plants provided power throughout the ship, with automatic switching that maintained power even if generators were destroyed. Communications systems included redundant routing so that messages could reach their destinations, even if primary circuits were severed. The contrast with Japanese battleship design philosophy was stark. Japanese designs emphasized offensive capability and crew efficiency, minimizing redundancy to save weight for armor and armament. This created vulnerabilities where single hits could cascade into catastrophic failures. When Musashi came under sustained air attack during the Battle of the Sibuyan Sea on October 24, 1944, torpedo hits flooded machinery spaces and disrupted power distribution. The damage control organization, smaller than American equivalents and lacking the equipment American damage control parties carried, struggled to contain flooding and maintain stability. Musashi absorbed at least 19 torpedo hits and 17 bomb hits over the course of several hours before finally capsizing and sinking. The prolonged death demonstrated both the incredible structural strength of her construction and the limitations of her damage control organization. With more extensive damage control capabilities, she might have survived to reach port, but Japanese doctrine had accepted reduced survivability as the price for maximizing combat power within displacement limitations. The fire control systems aboard Iowa-class battleships represented the integration of American radar development with mechanical computation refined through years of peacetime experimentation. The Mark 38 Director sat atop each main battery turret, housing both optical rangefinders with 26-foot base length and Mark 8 fire control radar. The Director weighed over 30 tons, requiring robust mounting that allowed it to rotate smoothly while tracking targets. Inside, operators monitored optical and radar data, selecting which source provided better information under current conditions. The Mark 8 radar transmitted pulses at a frequency of 9,000 MHz with peak power of 50 kilowatts. The transmitted pulse lasted 2 microseconds, with the receiver listening for echoes during gaps between pulses. The system could detect battleship-sized targets at ranges exceeding 45,000 yards under favorable conditions, though practical range for fire control was typically limited to 40,000 yards by atmospheric conditions and target size. The range resolution, the minimum distance between 2 targets that could be distinguished as separate contacts, was approximately 100 yards. This resolution was critical for fire control because it allowed the radar to detect shell splashes separately from targets. When salvos landed, radar detected both the target and the splashes, allowing operators to determine whether shells fell short, over, or straddled the target. This information fed into the fire control computers, which automatically calculated corrections for subsequent salvos. The closed-loop system meant accuracy improved with each salvo as computers refined their ballistic solutions based on observed fall of shot. The Mark IA fire control computer occupied a space roughly 12 feet long, 8 feet wide, and 8 feet tall below the main deck. Inside this space, thousands of gears, cams, and servo mechanisms continuously solved ballistic equations. The computer accepted inputs for target range, bearing, course, and speed from the Mark 38 Director. It accepted inputs for own ship's course, speed, and motion from gyro compasses and accelerometers. It accepted environmental data, including wind speed, air temperature, and barometric pressure from weather stations. Powder temperature from magazines affected muzzle velocity, so thermometers provided continuous temperature data. The computer synthesized all these inputs to calculate the ballistic trajectory shells would follow from gun muzzle to target. The calculations accounted for Earth's rotation, which affected projectile flight over the minutes required for shells to reach distant targets. They accounted for air density variations at different altitudes, which affected drag on projectiles as they climbed to peak altitude, then descended toward targets. They accounted for wind drift, which deflected shells horizontally during flight. They accounted for the motion of both firing ship and target, predicting where the target would be when shells arrived, rather than where it was when guns fired. The output from these calculations drove servo mechanisms that automatically positioned gun barrels to the calculated elevation and bearing. Gunners monitored the system but did not manually aim guns, except as backup if the automated system failed. When the director maintained lock on a target, and the computer had valid firing solution, guns fired automatically in salvos timed to spread impacts over a target area. The entire process, from target detection to rounds on target, happened faster than human crews could achieve through manual methods. Japanese fire control systems lacked this level of automation. The Type 94 rangefinder keeper, used aboard battleships Yamato and Nagato, was a sophisticated mechanical computer that assisted with ballistic calculations. But it required human operators to input range data from optical rangefinders and manually update target information as ranges changed. The calculations were accurate when operators had good data, but the system depended on optical rangefinders providing continuous accurate range information. Beyond 30,000 yards, optical rangefinders became unreliable regardless of operator skill. The result was that Japanese fire control accuracy degraded rapidly at extended ranges where Iowa-class fire control remained effective. At 20,000 yards, Japanese gunners using excellent optical equipment and well-trained crews could achieve accuracy comparable to American radar-directed fire. At 30,000 yards, Japanese optical fire control began struggling while American radar fire control maintained effectiveness. At 40,000 yards, Japanese optical fire control was essentially guesswork, while American radar fire control could still achieve meaningful hit probabilities. This disparity in effective range created tactical situations where Iowa-class battleships could engage Japanese battleships with near impunity. American ships could open fire at 40,000 yards, landing shells with sufficient accuracy to score hits, while Japanese return fire was ineffective. As ranges closed, American accuracy improved, while Japanese accuracy remained poor until ranges decreased to approximately 25,000 yards, where optical fire control began functioning effectively. But closing from 40,000 to 25,000 yards meant enduring 15 minutes or more of accurate American fire without effective counterfire. The Battle of Surigao Strait on October 25, 1944, demonstrated what happened when Japanese battleships attempted to close range against radar-equipped opponents. Vice Admiral Shoji Nishimura led a force including battleships Yamashiro and Fuso through Surigao Strait in darkness, attempting to penetrate Leyte Gulf from the south. Rear Admiral Jesse Oldendorf commanded American forces blocking the strait, including 6 battleships, 8 cruisers, and numerous destroyers. Oldendorf positioned his battleships across the northern end of the strait in a classic crossing the T formation, where his ships could bring all guns to bear against Nishimura's column, while Japanese ships could only fire forward batteries. But this was not traditional crossing the T executed through visual detection. American radar tracked Nishimura's approach for over an hour before guns opened fire. Fire control radars locked onto Japanese ships while they were still beyond visual range. When American battleships opened fire at approximately 0351 hours, their first salvos were radar-directed at ranges exceeding 20,000 yards. The American battleships included several older vessels that had been at Pearl Harbor during the Japanese attack, including West Virginia, Maryland, and Tennessee. These ships had been refitted with modern radar fire control systems during repairs and modernization. Their main batteries, ranging from 12-inch to 14-inch guns, opened fire with accuracy that astonished even American observers. West Virginia's radar fire control achieved hits with her first salvo, an accomplishment that would have been considered extraordinary luck with optical fire control at night. Japanese battleships Yamashiro and Fuso attempted to return fire, but could not locate American ships through optical systems in darkness. Their salvos were aimed at muzzle flashes and gun blast light, essentially unguided fire that had minimal chance of hitting targets at the ranges involved. Within 15 minutes, both Japanese battleships were catastrophically damaged and sinking. The engagement demonstrated that attempting to close range against radar-equipped battleships at night was suicide for forces relying on optical fire control. Had Iowa-class battleships been present at Surigao Strait, the engagement would have been even more one-sided. Their superior fire control systems and higher rates of fire would have allowed them to engage effectively at longer ranges and achieve hits more quickly. The older American battleships that actually fought the action proved that radar fire control provided decisive advantage. Iowa-class systems represented the apex of this technology, capabilities that exceeded even the impressive performance demonstrated at Surigao Strait. The psychological impact on Japanese naval officers who survived these encounters and understood their implications was profound. Captain Atsushi Oi, who served on battleship Haruna's staff and survived the war, wrote in post-war memoirs that learning about American radar fire control capabilities felt like discovering the rules of warfare had changed without notification. Everything Japanese officers had learned about battleship tactics assumed both sides would fight using optical fire control with similar effective ranges. Discovering that American ships could engage accurately at ranges where Japanese fire control was useless invalidated decades of tactical doctrine. The revelation came gradually through accumulated evidence rather than single dramatic moment. Combat reports mentioned American accuracy at improbable ranges. Survivors described shells arriving from directions where no ships were visible. Technical intelligence from captured equipment revealed radar capabilities Japanese engineers had not believed possible. The conclusion that emerged from this evidence was inescapable. American battleships possessed systematic technological advantages that Japanese forces could not overcome through tactical skill or superior training. This realization fundamentally undermined Japanese naval confidence in ways that extended beyond simple technical assessment. Japanese naval culture emphasized fighting spirit and warrior ethos as decisive factors in combat. Officers were taught that determination and tactical excellence could overcome material disadvantages. The demonstration that technology could create advantages so overwhelming that spirit and skill became irrelevant was psychologically devastating for officers whose entire careers had been built on assumptions that human factors determined combat outcomes. The Iowa-class battleships represented the culmination of American naval development, ships that integrated every technological advantage American industry and science could provide. They were not simply larger or more heavily armed than Japanese battleships. They were fundamentally different in conception, designed around technologies that changed how naval combat occurred rather than perfecting traditional methods. The radar fire control that allowed them to engage at 24 miles was not an incremental improvement, but a revolution in capability that rendered traditional battleship tactics obsolete. Japanese admirals watching shells fall from beyond the horizon were witnessing not just superior equipment, but the product of systematic American investment in research, development, and industrial application at scales Japanese industry could not match. The shock they experienced was not simply surprise at unexpected capability, but recognition that they had been fighting an enemy whose technological development had progressed so far beyond Japanese understanding that the naval war had been lost before many battles were even fought. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.